Hello everyone, welcome to chapter 5. So we just finished talking in chapter 4 about the idea of discrete random variables. These are random variables that have countable numbers, right? Numbers that go from 1 to 2, 3, 4, 5, but don't contain values in between. Now in chapter 5, we're talking about continuous random variables and then continuous probability distributions and functions. So real quick, we have just a brief recap here. When we're talking about random variables, we distinguish between the discrete and the continuous. So again, discrete is finite or countable, whereas continuous has infinitely many values that exist more on a scale or like a spectrum rather than individual numbers. So values of the discrete random variable can be plotted on a number line with space between each point, but the values of a continuous random variable can be plotted on a line in an uninterrupted fashion. So we don't have to just skip from number to number. We can take on values anywhere in between the whole numbers as well. So a quick example to get us back on track here with these types of variables. We're going to determine the following, whether they are discrete or continuous. Number of light bulbs that burn out in a room of 10 light bulbs in the next year. Of course, this is discrete because we're not going to have, 0.5 or, 0.75, whatever, of a light bulb. We have a whole number of light bulbs. And of course, our values go from 0 to 10, but they're all countable. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Number of leaves on a randomly selected oak tree. This one might seem like it could be continuous because there's a lot of them, but the leaves themselves are countable. If you had enough time and a strong amount of willpower to count those leaves, you could do it, and you would find that the value is discrete. It's a whole number of leaves. Okay. So this would be, so any positive integer. That would just be any positive value could potentially be the number of leaves on that tree. And then for part C, the length of time between calls to 911. We've talked about this before. Time exists on a continuous spectrum. We don't just jump from 1 minute to the next or from even 1 second to the next. Time exists at every moment in between all of those. So time is a continuous variable. And the length of time between calls could be any positive real number, not just integers, okay, not just those whole numbers, but it could be any positive real number. So when we talk about continuous probability distributions, and we looked at probability distributions for discrete random variables in chapter 4, and we had the table with all of the different values and their associated probabilities. But once we are working with continuous probability distributions, we don't have to jump from one value to the next. We don't need to set them up in a tabular method. We're going to be looking at them more as like smooth curves. So the probability density function, which is often abbreviated PDF, is represented in function notation. So we have f of x to represent the curve, where f of x is the function that corresponds to the graph. We use this density function to draw the graph of the probability distribution. So again, we're not looking at individual points like we were with, say, the binomial distribution. We're looking at a smooth curve because the values could happen in between those whole numbers. So we have every point accounted for in this curve. The area under this curve is given by a different function called the cumulative distribution function, abbreviated as CDF. This CDF, this cumulative distribution function, is used to evaluate probability as area. And this is a really important feature of what we're going to be talking about going forward. So I'm going to highlight it and box it for extra emphasis. When we're talking about continuous distributions for probabilities, the area under the curve is going to be the same as the probability. Okay? The area under the curve is the same as the probability. So here's a bunch of properties that'll kind of solidify this point. So for a continuous probability distribution, the outcomes are measured, not counted. The entire area under the curve and above the x-axis is equal to 1. Again, if we think about it in the context of probabilities, the sum of all the probabilities in the discrete version was 1, because all the probabilities add up to 1. So the area under the curve here must be equal to 1 because that has all the probabilities in it. Probability is found for intervals of x values rather than for individual x values. So we're talking intervals now. So, what is the probability that a value falls between 1 and 2? Instead of what is the probability that the value is 1 or is 2? So probability that x is between c and d gives us probability of it being on an interval. Okay, so this probability is, again, area under the curve, above the x-axis, to the right of c and left of d. So if you drew out like the number line, it would be in between c and d. An interesting feature about the continuous probability distribution, the probability of any one specific value occurring is actually equal to 0. So this is very different than the discrete, because in the discrete, we only were looking at one value at a time. But for continuous, the probability of one specific value happening by itself is going to actually be 0. Because when you think about it in terms of area, if we look at the area below the curve between C and C, so between a number and itself, there is no area, right? Like if you drew a curve and I said I want to find the area from here to here, and it's the exact same thing, there is no area there, meaning there is no probability individually. So what this tells us is that the probability of x being between c and d is the same as if you included included c and d in the interval. So whether you include the endpoints or exclude the endpoints, the probability is going to be the same. So moving into section 5.1, we're going to talk about continuous probability functions. Okay, so we know that a continuous probability distribution is going to give us some form of curve. All right, and the area under that curve is going to be a representative of a probability. So because we know that we're working with a curve and not just individual points, we call this a continuous probability function, because that function tells us what the curve will look like. Okay, so f of x equals, whatever. All right. So for example, consider the function f of x equals 1 over 20, where x is between 0 and 20, and x is a real number. construct a figure representing f of x, and find the probability that x is between 0 and 20. All right, so f of x is 1 over 20. So this is going to be, this is a constant function, right? It's the same thing as saying like f of x equals 5 or whatever. A constant function like this is going to represent a linear function, and not just any type of linear function, but specifically a horizontal linear function. So we're going to go up to the value 1 over 20. Obviously, this is not drawn to scale. It just makes it a little easier to see. And then we're going to have our horizontal line. And that goes all the way from 0 to 20. And when we're looking for the probability that x is between 0 and 20, what it's really asking us to do is find the area from 0 to 20. Because again, the area and the probability are the same thing when we're talking about continuous distributions. So we're really just looking for all of this area down here. So luckily, because it is a horizontal line on top, it just creates a rectangle. So we're going to be able to find this area. So this is, again, our probability of x here. The area of a rectangle can be found by taking base times height, length times width, however you want to think about it. The length down here is 20, right? It's 20 minus 0. The height of this is 1 over 20. And then a little bit of simplification here, we get 1. So the area between 0 and 20 under this curve was 1, which means that the probability is 1. So if the probability is 1, we know that that means this is a certainty, a certain event, right? Because they're telling us that x is between 0 and 20. So I know that 100% of my values fall between 0 and 20. That's basically what this 1 is giving us. Okay, it's giving us that likelihood that our value will fall between 0 and 20. But since those are all the values, then there's a 100% chance that this is what happens. If we take the same basic example, so we're still working with the 1 over 20, construct a figure representing f of x, representing the area where x is between 5 and 12, and we'll find that probability. So let's see, 5 is right here, 12 is going to be right about here. So we'll go ahead and draw that line there. And this, I'll just kind of put a little imaginary dotted line so we can see that it would continue on that way if we wanted it to, but we only care about the piece from 5 to 12. So this is the section we need to find the area of, and that'll tell us the probability, so the likelihood that our x value will fall between 5 and 12. So probability that x is between 5 and 12. Let's see, the width of that, well, the height's 1 over 20. That's the same. The width is 12 minus 5, which is 7. So we get 7 over 20, which is 0.35. So there's a 0.35 chance that our randomly selected value would fall between 5 and 12. Okay, so about a 35% chance of that happening. And we don't have to limit ourselves to, whole numbers here. We can work with any interval that we want across the whole thing. So if we take, again, a height of 1/20, the same formula. This time we go from 2.3 to 7.5. That's going to be right around there. Oops. Up to 7.5 is going to be right about in the middle there. So this area right here. Okay, now, of course, it would continue on, but again, we're only looking at that one portion that's been shaded. So probability that x is between 2.3 and 7.5. The height is still the same. The width is just the difference between these two. So we're going to get, that's 5.2 over 20, which if we go ahead and solve that out, that's 0.26. So a 26% chance that our value will fall in that range. So in general, the area under the continuous probability function f of x, where x is between c and d, so the area between a and b is given by taking b minus a times f of x. Okay, where a and b are somewhere in between the outer bounds of the formula. So you can see that's just what we did here. We had the function and then the b minus a right there. So this process will work anytime we're trying to find an area. And of course, right now we're working with straight lines. If they weren't straight lines, we might have to do a little bit of extra work to figure out how to find the area itself. But right now, we're just sticking with all horizontal stuff. So looking at section 5.2, we're going to talk a little bit about the uniform distribution. So the uniform distribution, we mentioned this briefly back in chapter 2. This is a type of distribution that is uniform. So when we say uniform, we mean that all the values occur the same amount of times, or at roughly the same amount of frequencies. This is a continuous probability distribution. So it's continuous, where all events are equally likely to occur. So if we want to find the probability density function, that PDF, we're going to use 1 over b minus a. So 1 over b minus a gives us the height of this probability density function. And that's with x going from a to b. Excuse me. Using the uniform distribution, we can calculate things like mean and standard deviation. And we're talking theoretical mean and theoretical standard deviation for these. And we'll see kind of how this works in a little bit with the examples. But basically, by computing theoretical mean and standard deviation, we're just looking at the overall behavior based on the endpoints. You can see here these formulas are just based off of the starting and ending points of that interval, regardless of what the specific values are between. Okay, so like for this example down here, the data that follow are the number of passengers on 35 different charter fishing boats. So the x bar is 7.9, the s is 4.33. So that's the mean and standard deviation for this data set, for this sample. The data follows a uniform distribution where all values between and including 0 and 14 are equally likely. We're going to state the values of A and B, write the distribution in its notation, and calculate the theoretical mean and standard deviation. So, we know that A and B are the smallest and largest values. Smallest value in here is 0. It pops up a couple times. Largest value is going to be 14, which also pops up a couple of times. So A is 0, B is 14. Our random variable x, we use the U, the capital U, to tell us that it is uniform, and then we'll go ahead and just put 0 and 14 for those bounds. Our probability density function, so that f of x, that's going to be 1 over b minus a, so 1 over 14 minus 0. So just 1 over 14. And this is for x between 0 and 14. Now for the mean and standard deviation, we could use these formulas. The mean works really quickly because you're just taking a plus b over 2. Standard deviation would need to work with a little bit of a calculator, but we can also set this up using technology. So I want to show you all how we can do that. So if we switch over to Desmos, we go to functions, and we scroll down to probability distributions right here. Right below the normal dist here, we have one that says uniform dist. We're going to click that. And notice Desmos says that the min is 0 and the max is 1. And it'll keep saying that until we tell it otherwise. So in this particular problem, we're going from 0 to 14, like that. So let me find that. There it is. So you can see we've got the line, right? This is the line of 1 over 14, and it goes from 0 to 14, right? And then the function dips back down again. We need the mean and standard deviation of this, the theoretical mean and standard deviation. So we could even just take the mean of this as is. So mean of that, and it tells us it's 7, which if you think about the calculation, it was 0 plus 14 all over 2. So it's 14 divided by 2, which is 7. And then if we want the standard deviation, we can also get that. That's about 4.041 approximately. So the mean is 7. Standard deviation is 4.041. Now, when it comes to actually finding probabilities with the uniform distribution, we're going to use the techniques that we saw in the previous section, but now also applying that using technology. So here we have the probability density of a random variable x is given in the figure below. From this density, what is the probability that x is greater than 1.38 or x is less than 0.26? Okay. So here we have our interval from 0 to 2. In order for us to start finding area of this, which is really what this is asking for, because remember, probability and area are the same thing. When it's continuous like this, we need the height in order to start finding areas here. But remember that the height of the uniform distribution, if I just scroll back really quick, that function height is 1 over b minus a. So in this problem, we have A is 0, B is 2. So this is 1/2. Right? That's 1 over 2 minus 0. So the height of this rectangle is 1/2. Okay? That's the function for our uniform distribution. And we are trying to find the probability that x is greater than 1.38. So that's going to be somewhere in here. So greater than that. Or less than 0.26. So that's going to be somewhere right about there. So we're trying to find, again, probability that x is less than 0.26 or x is greater than 1.38. And we can set this up like, our normal like probabilities, split it up across like addition because it's an OR probability, and then find the area of each of these pieces, just add them together. And when we're dealing with just like simple rectangles like this, you probably could just get the area real quick and just add them together. But we don't even really have to think about it that hard. What we can do instead is just take our uniform distribution function, our button here, put in the min and the max. So for this example, it was from 0 to 2. So let's find that. So there it is. And we can click on this cumulative probability button here, and it's going to give us some options. It's asking us what type of region we're looking for and what we want it to compute. So in this case, we want x to be less than 0.26 or greater than 1.38. So that's going to be an outer probability. So less than 0.26, greater than 1.38. That's our graph right there. Right? So that looks just like the one we have on our page. And you can see the probability right here is 0.44. And again, just as a reminder, these or equal to's right here, those don't change anything because with the continuous distribution, the or equal to does not add anything to the probability. So whether it's included or excluded, it's all the same thing. So that probability is 0.44. So we have about a 44% chance that a randomly selected value is in between, is less than 0.26 or is greater than 1.38. Now for this one, suppose that the value of a stock varies each day from 882 to 2117 with a uniform distribution. Find the third quartile. So 75% of all days, the stock is below what value? So we're going to have our function, our semi-horizontal line, and that's going to go from 882 to 2117. The height of this is just going to be 1 over 2117 minus 882. So it's 1 over b minus a. So that's going to be 1 over 12.35. And I know it's a little weird to leave a decimal inside a fraction. In this particular case, since I want to be able to see it as the 1 over, just so we remember where it came from, we can go ahead and leave this as is. The calculator will help us later with that. So we are trying to find the third quartile. So somewhere over here is Q3. Okay, that's going to be this value. Now, the way that these problems are structured, they either give you the x values and ask you for the area, the probabilities, or they give you the area with the probabilities and ask you for the x value. This is one of those kind of flipped cases. So we know now that because it's the third quartile, remember how we define the quartiles? They break the data up into 25% chunks. So we have here, for the third quartile, 75% of the data falls below this value. So we know this area is 0.75. And we're trying to figure out what Q3 is. Okay, so again, looking at the difference, before this, we knew the x values, and we were trying to find the area. Now, we know the area, and we're trying to find the x value. Okay, so we know probability that x is less than Q3, whatever that is 0.75. So we're going to find Q3 and round to the nearest cent. Luckily, the technology can help us out here. So this particular uniform distribution is going from 882 up to 2117. So what we're going to do, instead of looking at the area, we want to find the bounds. Okay. So we want to find bounds, and the area we're currently looking at is 75% to the left. So we're going to do left, and this time we get to type in what we want the area to be. That's 0.75. And right here, we have that upper bound. So this is the x value. That is the upper bound on this 0.75 area. That is Q3. That is the third quartile. So we get, and this is in dollars, 18.08. So that means 75% of our data in this stock would be below $18.08. All right, and we'll take a look at one more example, kind of similar. The lengths of a professor's classes have a continuous uniform distribution between 49.2 minutes and 55.5 minutes. We randomly select one class and find that the probability for that class to run longer than C minutes is 52.9%. In other words, it's 0.529. Find the length of a randomly selected class. So that is of that randomly selected class. So that's find C. So we know that their classes run from 49.2. So I'll kind of shift this up a little bit here. So we'll say 49.2 up to 55.5. So it's uniform distribution, so it's that horizontal line. This value, again, is 1 over b minus a. So that's going to be 1 over 6.3 for our height. And we're in a similar situation here where they have now given us the area and we need to find the x value. So we know that probability of x greater than c, so I'll just put it right around here. So that's c. This area, this probability is 0.529. And now our job is to find C. All right, so let's take a look. We're going to go back, start fresh here, 49.2 up to 55.5. And we want the bound when we're looking at a right area. Okay, that's the greater than. And right of 0.529. So find that. Here it is. Okay, so 0.529 is the area inside that shaded region. And the C value is going to be that 52.17 rounded. So 52.17 minutes. So if we have a randomly selected class where its length is going to have 52.9% of classes longer than it, okay, that's 52.9% above this class length, then that class length is going to be 52.17 minutes. So we're drawing connections here with continuous random variables, continuous probability distributions, seeing how we're looking at, curves now. We're looking at smooth lines, not individual distinct points like we did with discrete. And we're looking at the uniform distribution and how we can compute probabilities using area, and then calculate X values also using the technology. But that brings us to the end of Chapter 5. We'll be back in Chapter 6 to talk about our primary distribution, which is the normal distribution. So I will talk with you all in Chapter 6.